Hey folks, in this example we're going to calculate the moment of inertia of a square, and it's a square that has two dimensions in which we have 2L on both sides. We're going to calculate the moment of inertia about the center of mass G, and then do this in the body fixed basis. So it's in the reference frame in which we have a B1 and a B2 direction. And in addition, we're going to assume that it has mass m and then a uniform density rho. So our equation for this is the inertia about the center of mass, and this is for planar motion, is the integral across the body of the norm of the position vector of our differential element with respect to the center of mass squared, and integrating that over all the differential masses. And this is where dm, our differential element, is equal to rho dv, and dv, because we're in planar motion, has units of mass divided by length squared. And so we need to add some coordinates to this, and here we have our differential element, dm, and it's a length x away from the B2 axis and a distance y vertically away from the B1 axis. And so the position vector r dm with respect to g will be x in the B1 direction plus y in the B2 direction. So we'll fill in our moment of inertia formula, in which we're going to have a double integral of x in the B1 plus y in the B2. We're going to take the norm of this, square it, and then multiply rho dy dx. And then we need to put bounds on this. It's dy dx. So for our x bounds, we're going to go from negative L to positive L. And for dy, we're going to move our differential element from negative L to positive L. So negative L to positive L, and negative L to positive L. So continuing on, our norm, double integral, our norm is x squared plus y squared. This is rho dx dy. So negative L to positive L. And so we'll first integrate with respect to x because it's on the inside of the dy. And so when we integrate with respect to x and apply the fundamental theorem of calculus, we get the expression 2/3 L cubed plus 2L squared y on the inside. And we still need to integrate with respect to y. And after this we get the final expression, or the almost final expression, of rho multiplied times 4/3 L to the fourth plus 4/3 L to the fourth after integrating with respect to y and applying the fundamental theorem of calculus. So we get 8/3 rho L to the fourth. Now recall that we can't just leave this in terms of rho, but instead we need to, we have the mass of the objects m, and so we set the relationship between the mass and the density, rho, and it's uniform density, so its mass is equal to rho multiplied times the area. So this is rho, and then the area is 2L multiplied by 2L. So this is 4L squared. And when we substitute this in, well, we'll solve for rho, m divided by 4L squared. And now substituting in, our moment of inertia about the center of mass is equal to 8/3 m over 4L squared multiplied times L to the fourth. And so we get a final expression of 2/3 mL squared. And so for a square, as we've seen this in this example, the rotational moment of inertia, if this square is resisting the rotation, is 2/3 mL squared. Always double check your units, in which we have a mass multiplied times two lengths, so mass length squared are units for the mass moment of inertia. And so we've just worked through an example using Cartesian coordinates to calculate the moment of inertia using our expression that we developed from angular momentum in the last screencast.